All right, so for the this activity, Fired Up, you guys, I'm going to show you guys a series of like 6 demonstrations. All right, I'll tell you right now, the first couple are not the coolest in the world, but they get better as we go along. Now, for each one on your table, there are 4 things I want you to please fill in. First column, what do you notice? Basically, just describe what you see in the demonstration. Second column, relate it to something else. Okay, what does it remind you of? I want you to relate it to something outside the classroom, perhaps, something in your life. That way, when you think of one thing, you can associate it with the other. Third column is, what do you wonder about? Think of a question. Think of something that you might be curious about, somehow related with that particular demonstration. And then the last column is where I want you guys to please come up with either an answer to that question, a possible answer, or come up with a basically an explanation for the demonstration. Try to explain why what happens. All right, anything that makes sense to you works. Now, after that, there's a series, I think, 4 or 5 questions. The first 4, I think it is, those are answering questions based upon your observations. If you scroll down and look at those real fast, a lot of people have difficulty answering those questions because they don't read the questions carefully. For example, the first one, I believe, is asking which has a higher temperature in each of these demonstrations, the reactants or the products. Now, the answer is going to be either reactants or products. However, if you don't read all the way to the end of the question, some people might think that you're supposed to put in, which of the demonstrations, the water bottle or the magnesium or whatever, okay? That's not what it's asking. You answer each of those with either reactants or products and then explain why you think that is. Now remember, reactants are what you start off with. Those are the chemicals that you begin with. And the products are what you produce. Those are the chemicals that are there after the reaction is done, but were not there before. All right? Now, the first demonstration is going to be really lame. It is literally lighting a match. Now, to make it a little more interesting, did you guys know that there are 2 types of matches? Strike anywhere and safety matches. Are you guys aware of that? Probably not. You probably don't sit up nights thinking about matches, but it's true. Now, the old-fashioned kind are called strike anywhere. If you have some of those, all you have to do is apply some friction to them and they will light. So you can light them against the wall or on some sidewalk. I even know some pyromaniacs that light them on their teeth or even using like a fingernail to apply the friction, and they can light them that way. Okay? I'm not saying I did it, but I'm not saying I haven't. Now, but a safety match has to be struck. It only gets lit if you strike it on the actual friction pad that comes with the package. And the reason why they have safety matches is it makes it a little bit more challenging for like little kids to light fires and burn down houses and things like that. Now, the reason, the way it works, I think is kind of interesting. In order for this flare-up type reaction to occur, you need 3 reactants. One of them is oxygen. You always need oxygen for any type of fire, all right? And then there's 2 other reactants. One is a whitish substance called sulfur, all right? And the other one is kind of a reddish one called phosphorus. Now, you have to have both of those combined with the oxygen and then apply some friction to get the reaction started. Well, in a strike anywhere match, both of those chemicals are right there on the match head. So if you see a match that has like multiple colors on the match head, that's probably a strike anywhere match. Whereas safety matches like these only have 1 color. Like this one's just white. So this has the sulfur on the match head. The red phosphorus is embedded in the strike pad. So you have to strike it against there in order to mix the chemicals in order to start the fire. I thought that was kind of interesting. Hopefully you're not too bored. But anyways, that's going on with that. Now, the second demo I'm going to do is, and this is exciting, I'm going to light a candle. Right? Exciting. Now, first of all, what's actually burning in a candle? The wick burns a little bit, but primarily it's not the wick. What's the fuel for a candle? You have oxygen, obviously, but the wax. Excellent. All right, it's all about the wax. Now, the wick, all that does is it takes the liquid wax and draws it up so that oxygen can get at it from all angles. It increases the surface area of the wax. If you just take a puddle of wax and try to light it on fire, it doesn't burn very well. It's very hard to burn just pure wax. But with the wick, it allows it to be drawn up and it makes it a lot more surface area so it can actually burn. Okay? Now, there's a cool effect that I want you guys to see. And especially back there, it's kind of hard. You have to be kind of close up. So I'm going to ask you guys to kind of come a little bit closer. Don't block the camera. But come a little bit closer so you can see this. It's kind of a neat trick if you've never seen it. So come as close as you can. It requires standing up. So I'm going to show you, right about there is perfect, okay? You can just stand up, or I want you guys to be able to see this. Maybe come over here. I want you guys to be able to see this. Now, first of all, here's the lighting of a match, because you've never seen that before. Ready? Ooh, impressive, right? Now, the candle, I will light the candle. Now, here's the cool effect. I want to see if this works. It sometimes works, sometimes it doesn't. You guys ready? Watch carefully. Do you see it light without me touching it? It doesn't do it a second time. But you guys saw that, right? Not even touching it. What happens is the smoke that you see when you blow out a candle, that's actually mostly little tiny droplets of unburned wax that got drawn up, and then when it got extinguished, they weren't burned, and they just go up kind of like a little cloud with little tiny droplets of wax. And when you bring the fire close to it, it actually travels down, lighting one droplet after another, and travels down and relights the wick. I've seen a video where they actually do it like from this far away. I haven't been able to do that, but it's really cool. But anyways, that's kind of the neat effect I wanted you guys to see. Thank you so much. I want to make sure you guys saw that. So take a minute and go ahead and write down those things, all right? Take a minute. And we're going to stop each one. So the next demonstration is called the water bottle. And it involves a Sparkletts water bottle and some isopropyl alcohol. Now, do you guys know this by a different name? No, it's actually a good guess. It's not hydrogen peroxide. Has anyone ever heard it called rubbing alcohol? Okay, it's a common name for it. Raise your hand if you've heard it called rubbing alcohol. All right, cool. Let's do that. Why is it called rubbing alcohol? Does anyone know why? It's an old-fashioned name for it. Most people think it's because you rub it on a wound or whatever, you disinfect it. That's not it. It is, well, let's put it this way. Why do we sweat? What's the purpose of sweating? Good guess, but no. Sorry. Good guess. Purpose of sweating is how our species cools off. Perfect. Because you sweat and you get water on your skin, and then it evaporates. When it evaporates, it takes the heat away. It's the whole purpose of sweat, right? Or at least the primary purpose of sweat. Which evaporates faster, water or alcohol? Which do you think evaporates faster based upon what your experiences are? Alcohol, right? Anything that you can actually smell very well tends to evaporate very quickly. Gasoline evaporates even faster, okay? If you remember back from first quarter, water molecules have hydrogen bonds between them, which means that they stick together. They don't like separating very well. They will evaporate into a gas, but not as fast as alcohol, which the bonds between the molecules are not as strong. They're just like dipole-dipole attraction. So those do not, that evaporates faster. Gasoline doesn't even have dipole-dipole attraction, and the molecules separate very, very quickly. That's why if you're filling up a gas tank and you spill on a hot day a little bit of gas on the ground, boom, you look down, it just evaporates in front of you, okay? It's just gone. So evaporation cools things off, and alcohol evaporates faster. So back in the day, before they had reliable fever-reducing medicine, especially for like little kids, they would, if your fever gets too high, it can actually be very dangerous. If you're sick, fevers themselves are actually good for you. All right, that's something a lot of people don't know. A low-grade fever or a fever like 101, whatever, that's actually very good for your body because it elevates your temperature and it causes your immune system to operate more efficiently, and it helps you fight off the infection. However, the fever itself, if it gets up too high, 105, 106, 107, that itself can cause brain damage and even death. So you want a little bit of a fever, but too much can be dangerous. And especially if you're dealing with like a little kid, like 2, 3, 4-year-old little kid, for whatever reason, they can run really high fevers. And it gets really scary for them, all right, or for the parents primarily. They can run really high fevers. So back in the day, if you needed to reduce a fever and you didn't have the medication, you can take rubbing alcohol, put it on a washcloth, rub it all over the kid's body, and as it evaporates, it cools the kid off very, very rapidly. So that's why it's called rubbing alcohol, in order to evaporate and reduce fevers. See, you learned something you didn't know. You didn't care, but you learned something you didn't know. All right. So what I'm going to do, back to the actual demonstration, is I'm going to take the water bottle and just going to squirt a little bit in. Not a lot, just a little bit. And then, now what I'm doing here is I'm spreading it out. I'm increasing, just like the wick, it increases starts with an S, ends with area. Surface area, okay? It increases the surface area. Now, I can only do this once, so make sure you watch carefully. Okay. Goggles. Once again. Three, two, one. Ta-da! So that's the water bottle then. Now, the coolest thing is, or not the coolest thing, that was the coolest thing, but an interesting thing is, I don't know if you guys can see this, it's all foggy in there now. You guys see that? And what a lot of people don't understand or know, because they haven't taken chemistry, is that whenever you have true combustion is whenever you burn an organic compound, like alcohol, or wood, or a match, or whatever, it always produces two products. One is carbon dioxide, which is, the main reason for global warming. And two is water. Fire produces water. And usually it's so hot, it's a gas, you don't see it. But here, it's kind of been trapped, and it's cooling off along the outsides of the container. And it has condensed back down to a liquid. And that is the water that was produced by that reaction. Kind of trick. Did you guys ever see on a cold morning, like a car exhaust, it gives off a lot of, looks like smoke? It's actually steam, right, that is coming out of the tailpipe. And it's hitting the cold air, condensing to little tiny droplets, which you can actually see. You can't see a water vapor. It's invisible. But steam, you can, because it's actually the little tiny liquid droplets, like the smoke on the candle, liquid droplets, those you can see. They're just held up in the air because they're warmer and they rise up and all that. All right? So go ahead. Any questions? Go and write down your observations and so forth for that one. All right, for the next demonstration, the magnesium, on this one, I have a question for you. Does metal burn? Does metal burn, like, pots and pans and things like that? Does metal burn? I'm seeing most of you guys shaking your head. But you think there's a trick to it, and you're right, there is, all right? I have here a little piece of metal. It's a magnesium, right? Number 12 on the periodic table. And if you notice, it's on the outside of the periodic table. If you remember from first quarter, right? Things on the outside of the periodic table tend to be more reactive than the things in the middle, right? Now, I have, I'm going to light my lab burner. Gas to go through the tube. Nice hot flame. By the way, notice how thin the metal is? If it's thin, that means it starts with an S, ends with area. Surface area is going to be greater than it would if it, compared to its volume, it's going to be greater. So you're increasing the surface area by it being thin. Now don't look directly at it, right? But it's like it's as bright as the sun. The smoke that's coming off the top, that is the oxide of the magnesium. It's magnesium oxide, MgO. And while technically not combustion, because it was not organic compound, it is a rapid oxidation. And when you see a flame, we call that burning. So in effect, you are burning the magnesium. Well, what about an element like iron, which is towards the middle of the periodic table? Remember, those guys aren't very reactive at all. Well, even iron will burn under the right circumstances. Here I have a piece of steel wool, like for scrubbing dishes and so forth. So I got some steel wool, again, a hot flame. And if you see the sparks flying off and so forth, that is it actually burning. And what's going on here is it's rapidly oxidizing. Now, normally when iron oxidizes, we call that rusting. If it does it slowly. I'm doing it quickly, so I'm just rapidly oxidizing it or rapidly rusting it. And that's that one, right? So for this one, I have a balloon. The balloon is filled with methane, which is the same gas that comes out of the pipes for our lab burners. So, light a lab burner. Good flame on it. You guys ready? 3, 2, 1. Ta-da! Right. And that's the balloon one. Do you guys feel the heat?
Yeah.
Awesome. Which is the benefit of actually showing up. If you were closer, not worried about your cashmere jacket, whatever, then you would have felt the heat even more. What do we need for fire? We need
White phosphorus.
no. For any type of fire, we need two things primarily. What are they?
Oxygen.
Oxygen, good, and starts with an F, ends with fuel. Fuel. Now in here, the fuel is sugar, plain old powdered sugar. And to provide the oxygen, I also have a chemical called potassium nitrate, KNO3. And it's that O3, it's an oxidizer. It actually provides its own oxygen in addition to the oxygen in the air around us. Once you get this started, technically, you don't need oxygen. It can almost be done in a vacuum all by itself. We're going to see if we can't get this lit and going here. Goggles. Nope. Try one more time. There you go. And come closer so you can see inside. It looks really cool inside. And see if you can smell the smoke at all.
The smoke smells stinky.
It's a little bit stinky. Does anyone know what it smells like?
It's like a marshmallow.
Good, like burnt marshmallow, which is basically what we have here, burnt sugar. Now, it is a very hot reaction. The first time I did this in like an aluminum can in my driveway, and it just melted the can right down the slag. But you can actually do this yourself at home. The material is obviously sugar, and the potassium nitrate can be found at plant nurseries. It's in stump remover. And online, there's all sorts of formulas for it. Just make sure you do it safely and do it where you have plenty of room and not going to start the next big forest fire or anything. All right. So, anyways, that is that.